Carbon neutrality is essential. It's very, very difficult to achieve. We need game-changing technologies in key areas such as carbon capture, for example.
Carbon capture is based on very sophisticated technologies, and it implies sophisticated materials. We need to perform accurate simulation in order to predict their properties.
Reducing CO2 from the atmosphere requires development of new disruptive solutions. At TotalEnergies, we believe that one such technology is going to be quantum computing.
TotalEnergies is a multi-energy company. It is a worldwide company. We have to have a net zero society by 2050. And TotalEnergies is fully committed to this scenario. Carbon capture, transport, storage, and its reutilization is key. Carbon capture is key because it is the most expensive brick in a CCS chain. So we have to decrease the costs. The key for carbon capture is finding the needle in the haystack, the right material, the optimal material, to have this cheap capture.
CO2 capture is the process of separating CO2 from other components of either an industrial flue gas or directly from the air by using media, so usually a liquid solvent.
The principle is to mix the CO2 flue gas with the solvent. The CO2 will be extracted from the solvent at high purity, and the solvent will be regenerated in a loop system and can be reused to capture more CO2.
Today, we're looking at higher technology readiness level areas, and we have a very nice demonstration project working with ArcelorMittal in Dunkirk. But equally, we are developing low technology readiness level projects. This would be, for example, the development of new materials.
In TotalEnergies, we are working on the three aspects, trying to find the optimal between the best material, the best way to contact it, and the best process. Traditionally, we work more with experimental and process modeling, but the technologies of molecular and atomistic modeling are complementary.
We use machine learning to search new family of materials. There is 3 per scales, the sub-nanoscale, nanoscale, the mesoscale, the macroscale. We start focus on atomistic mechanism in nanopores or sub-nanopores, feeding the one at larger scales with parameters carefully determined at the smaller scales and climb scales step by step. All this stuff is made possible by really huge computing.
TotalEnergies has used supercomputing for many years, and we continue to do so. We have facilities in Pau, France, and in Houston, Texas, where we have dedicated teams that help us to perform our parallel computations. For carbon capture, we need to model interaction between CO2 and the absorbing material microscopically in order to derive macroscopic properties that will enable us to optimize those materials. And to do that, we need massively parallel computers. We use traditional high-performance computing, and we also have a dedicated team that is specially working on quantum computing based in Saclay, close to Paris, where a large ecosystem of high-tech companies have settled over the past few years.
Unlike classical computers, which operate with classical bits, which can be in a 0 and 1, quantum computers operate with qubits, which can be in a superposition of 0 and 1. Doing computation with quantum bits or qubits enables one to do computation in an unprecedented parallel scale which does not exist in the classical world. We applied quantum computing to these materials called meta-organic frameworks. To be more specific, we developed an approach which allows us to treat large unit cells of materials such as meta-organic frameworks and to probe these unit cells of materials for their carbon capture capabilities. We teamed up with Quantinuum, a startup from the United Kingdom, which worked together with researchers from TotalEnergies in synergy to drive this work toward publication in EPJ Quantum Technologies.
Marco is able to determine really accurately some parameters. An important one, for example, is point charge on each atom of the structures, which is absolutely key to determine water adsorption, This was really a key finding for us. We are able in some materials to use water to improve the CO2 capture.
Quantum computing will help us to unlock a lot of problems that we currently have in the simulation. And since carbon capture is very demanding in such kind of simulation, a lot of breakthroughs are expected.
The most exciting thing about quantum computing in the future, this is the unknown. This is the fact that today I cannot even start imagining what solutions are going to be there 10 or 15 years from now in the domain of quantum computing. And I mean this in the realm of climate change and carbon capture and in other realms also.